Hi, and welcome to this third part of contextualized extraction thanks to kernel memory. The idea is I have a complex document like a manual of a vacuum robot cleaner, and I have my use case. I want let an help desk answer question from a user. So the first step in the first video, I demonstrate how you can integrate in kernel memory custom text extraction thanks to Llama Cloud parse functionalities. This produces well-structured markdown in which I'm not extracting the real text of the document, but I'm extracting something that is manipulated by a large language model. So I ask large language model to extract a series of question and answer. Thanks to this well-known structure, I've created a custom text chunker that instead of splitting text into chunk of fixed token, uses the fact that I have structured text extract from the previous step, so I can extract question and answer separately. So each question and answer become one single chunk, and this is especially important because it does not split pieces of text that is meant to be in together. So I have a series of question answer, and all the chunk contains one question and the relative answer. Now in this third part, I finish this journey demonstrating how in this situation it is much more useful to use a custom embedding to generate embedding only with the question part of the chunk. In this example, I'm using a customized version of the embedding generator that is based on the original code of kernel memory, but I'm simply configuring with a small difference that for each pieces of text, instead of creating embedding for the entire chunk, I have a function that takes the text from the chunk and is capable of extracting a little part, a different part to get into the embedding. As you can see, the last parameter is extract text from chunk. That is my function that will take the entire chunk and extract the only part of the chunk that I want to send to OpenAI to create embedding with the embedding generator. Well, the extract text from chunk is really simple, and it simply split the text into line and take the first line. And now I'm going to run the example and show you why I've done this choosing, why this is the right path for this specific scenario. Now, if you remember the last example, what I got in result from the contextualized text extraction from Llama parse is a series of question and answer extracted by a PDF document. So my goal is not to extract the exact text, but taking advantage of Llama parse functionalities give an exact specification. I want to extract all the question and answer you can find from this document. So as you can see, and I want it to be separated by dashes. So as you can see, I have a very well-structured output. This gives us the ability to use a custom parser that analyzes the text output and separate all the chunk, splitting by the 4 dashes, because that was the instruction I gave to Llama parse. Now I have all chunks that are composed by a question and an answer. Now, if you remember how by-encoding works, you could understand that this basic strategy of taking all this text and passing all this text to OpenAI or to other embedding generator to generate an embedding and do a vector search probably is not the best option. Now, if you remember how by-encoding works, how vector search work, it works using an embedding model. The embedding model captures the context of a piece of text and stores and generates a vector. We store those vectors in a vector database. And then when the user make a question, we create an embedding of the question and we look in the database for the pieces of text that has the nearest vector, hoping that we find the pieces of text that are more near the embedding of the question. Now, if I already know that with contextualized extraction, each chunk is composed by a question and is highlighted in red in this slide, and then the answer, it is much more useful if when you create the embed of these pieces of text, you generate the embedding only for the question part, because it's much more common that you find similar question of the user and question stored in database. instead of looking for a vector of the answer to the question. And this is valid only because I have this very specific extraction made by llama parse that generate question and answer directly using a large language model. So it is common for me not to generate embed of the entire text, but only of the question. And also, if I want to index for a keyword search, I will index only the question part of these pieces of text, because it's much more probably that the word, the keyword and the text that I can find in the question, it's matched with the question of the user, not the answer. So thanks to kernel memory, doing this modification is straightforward. Now, as you can see, I have my breakpoint in the part of the embedding handler that actually is using OpenAI to create the embedding. The only difference is I have a batch, because it's much more efficient to work in batch. And for each batch, I have a series of partition. And all partition have the context of the partition, that is the content. Now I take each partition, I take the content, and I pass to the extract text to embed async. It's the function I've used in the constructor that basically only take the first line of the chunk, because as I told you before, all chunks are composed by a first line, the question, and then the answer. And that this is generated this way because I asked to llama parse exactly this kind of markdown. So I'm pretty sure that this is correct. So I have pinned the first elements just to show you that I've created an array of string. Each element is the text I will send to OpenAI for embedding, and for each element, I only have the question, the first line. So in this example, it's very much powerful to take only a small part of the chunk, because I know that the first line is the question. And so it's much more efficient to store in vector or in keyword only the question part, because there's a much more higher probability that the vector of the single question of the chunk is near the vector of the question of the user that has no answer. That is also really useful if you are using an embedding model, not the OpenAI, but an embedding model that suffers from asymmetry. So it works well when the text is of similar length. So instead of embedding the whole chunk with question and answer, I will embed only the part of the question. So it is much more similar in length, probably, to the final question of the user. In the end, I always have vector inside the vector database. This is the text vector database, the test vector database that can be used in kernel memory to store vector in your file system, and it's useful for quick debugging. And as you can see, I have the original text, but thanks to my embedding generator, in reality, the embedding is created only using the question part of the chunk. Even if the database contains the whole chunk text, so question and answer, I assure that the generated vector is generated only with the question. That is really important because I want the vector to be generated with the question, but in the database, I want the entire text to be indexed, because my purpose is when I have a question of the user, I'm trying to find the right answer matching the question part of the chunk. Now I could also create another step in the pipeline that will remove the question directly from the chunk, but I prefer to left the question in the chunk because it's much more efficient, even for the large language model, to have chunk that contains question and answer. It gives more context. And thanks to this example, it is clear how kernel memory is really, really flexible and allow you to intervene on every moment of indexing. You can use a custom text extractor from your binary file. You can use a custom chunker, and you can even change how you create the vector, the embedding for each chunk to maximize your retrieval during the retrieval phase of RAG. To recap, I've created a custom module that is capable of extracting text using llama parse, giving specific instruction like I want you to extract not the original text, but want to extract a series of questions and answers in Markdown with a specific format. So I then move to a custom chunker that is capable of creating a chunk in which each chunk is a single question and the corresponding answer. And finally, when I want to generate the embedding for the chunk, I only use the question part for the embedding to maximize retrieval. And this concludes this first 3-part example in which I show you how to use llama parse. In the next video and in the next series of video, I'll demonstrate other technique that can be used to extract text from a binary file that generate a text that is much more similar to the original text, or it is much more structured to avoid losing structure during the text extraction. Stay tuned, I'm waiting you for the next video.